And Yuri Kroyan is going to present on the performance of advanced fuels in end-use sectors. As I indicated to the audience, please do use the chat to suggest areas where we could look to collaborate. Yuri, the floor is yours. You're very welcome.
Hello and good morning, good afternoon and good evening. Thank you very much, Brian, for introduction. I will now try to share my screen. Let's see whether it works. Can you see my screen?
Perfect.
Okay. So my name is Yuri Kroyan, and I'm a doctoral candidate from Aalto University. Today I have a pleasure to present you end-use performance of alternative fuels in various sectors, including aviation, on-road, and marine transportation. But first, just a brief words about my research group. So I'm a doctoral candidate from the research group of energy conversion, which is headed by Professor Martti Larmi, but we have 4 professors in total and about 50 researchers working on various aspects in circular economy and energy and sustainability. And my agenda is to show the magnitude of the decarbonization challenge in transport sector, and then the performance of RES fuels in end-use sectors, some recommendations, and some few options that came into my mind that we could perhaps collaborate. So when looking into the total energy used in transport, it was 2.8 gigatons of oil equivalent in 2017. Please take this blue area as area that represents this 2.8 gigatons. So the black part of that area are oil products. Here we see the natural gas, biofuels and waste, and electricity. When we turn it into the percentage, we see that it's over 95–96% fossil. And when speaking about the various technologies, we see that we need all of them to go hand in hand, because there is the magnitude of the decarbonization is so big that we unfortunately at the present state have no luxury of selection which one to go, either this or that. I think we should go with all of them, because on 2050 the challenge will be much bigger. And the known fact is that we can use same feedstocks to produce either electricity or liquid fuels, and then use it to power the mobility. So in our eyes, we should rather focus on feedstocks to eliminate unsustainable feedstock as the most important priority, to bring the real change from the environmental perspective. And the very important over here are 2 things: the life cycle, greenhouse gas emission, and price of the reduction of those CO2 emissions. And as we see on the left-hand side, we have this kind of life cycle analysis for the internal combustion engine running on fossil, battery electric vehicle 80 kilowatt hours, then a hybrid electric vehicle, battery electric vehicle 40, and internal combustion engine running on HVO. So as we see, the thing that we have a tailpipe in the car does not mean necessarily that we have higher emissions. If we just substitute the fuel into the more sustainable one, then we might end up having emissions even lower than in the case of the electric vehicles. So in that respect, we need to take into account the life cycle, not tailpipe emissions, to bring the real change and meet our climate targets. And another important factor is the need for liquid fuels versus electrification. So as we know, the electrification is the easiest in the light duty vehicles, and it grows with the rail, heavy duty, marine and aviation towards most difficult, and opposite is the need for liquid fuels. An advanced fuel project is the one that we were working on. It's a part of EU H2020 projects, and it's a coordination and support action from EU Commission. The target is to facilitate market rollout of advanced liquid biofuels in transport sector between 2020 and 2030 and beyond. And advanced fuel project focuses on various on the whole value chain. But we as Aalto are the only partners focusing on the end use. So how those alternative fuels perform in end use sectors. And we had a task to bridge fuel properties with engine performance. We know that we have different engines, light duty, heavy duty, marine, aviation. They use different fuels. Those fuels have different properties, and different properties are important for different sectors. So what we did basically is that we took data when standard fuel marked as S was blended with some renewable fuel marked as R. Of course, that blend end up in different fuel properties than standard fuel alone, and then yielded in the different fuel consumption and different emissions. Our task was to find the bridge between directly fuel properties and engine performance, not fuel components, but fuel properties and engine performance. And we developed 7 models for air, land, and marine transportation. We equipped these all models into the user-friendly tool under the advanced fuel.aalto.fi. I will get back to the tool a little bit later stages of my presentation. So basically we developed model for jet engines, spark ignition light duty engines, compression ignition engines, flexi-fuel vehicles, fuel cell vehicles, heavy duty compression ignition, and marine compression ignition. We've been mainly using the multilinear regression with quantitative analysis. So statistics involved to determine the significant properties. And we developed linear models that represent the effect of the most significant properties that survived the modeling procedure. And all input and output parameters are represented as percentage changes relative to the reference fuel. So for example, diesel for compression ignition, gasoline for spark ignition, jet A1 for jet fuels, and heavy fuel oil for marine. And let me show you some examples. So for example, model for spark ignition engines looks like this. We have the effect of the research octane number, density, lower heating value, and oxygen content. For those who don't know, research octane number is a measure of the reactivity of the fuel, so how eager it is to auto-ignite under the compression. The higher the RON, the lower the better auto-ignition properties, so fuel doesn't auto-ignite before the spark. We know that different fuels have different properties, and we, based on the real data taken from different labs, so that there were chases dyno runs of the new European driving cycles from different parts of the world. We took this data, created single matrix, did this modeling, and we achieved model with pretty high R-square. And we did the same also for the flexi fuel fleet. But what's interesting over here is that for example, in case of alcohols, we see that E85 can have about 35% higher fuel consumption dependent on the actual concentration of the ethanol. So E85 has very, let's say, wide range. It could be 70% ethanol inside the blend and it's still called E85, or the upper level like 85% and still called 85. So a lot depends on the actual content on ethanol, the fuel consumption changes. But what's interesting, we see here tailpipe CO2 emission. These are not well to wheel, but tank to wheel CO2 emission, what we see over here. And even despite this higher fuel consumption, as high as, for example, 36% or so, 35, in the standard fleet, we see that the CO2 emissions are still lower than for the, and we talk about the raw CO2 emission, are still lower than for the gasoline itself. And then when we take into account the well to tank part, sustainability in that part, then the reduction is tremendous. Of course, these effects of the alcohol blends in flexi-fuel vehicles are a little bit more effective, better, because flexi-fuel vehicles can adjust the engine so that they can utilize higher RON a little bit better than standard engines. So they can retire a little bit the spark timing, increase the boost pressure, two different kind of dependent on the engine map and fuel engine loop. They can adjust a little bit better over here and utilize these effects. And of course, it decrease the CO2 emission, raw CO2 emission of those ethanol blends, alcohol blends in general, even further. Moving forward, compression ignition side, we see the effect of the cetane number, density, and lower heating value mass base. Cetane number, here is the property also similar to, it tells all about the reactivity. The higher cetane number, the more reactive fuel is. And for spark ignition engines, we don't want reactive fuels. But in the compression ignition engines, we want reactive fuels. We want that fuel will ignite during the compression stroke. As there is no spark, it's compression ignition mode. And here we see the model, also developed based on the European driving cycle chases dyno run experimental data. The model, again, pretty high R-square. And what's interesting over here is that we can see HVO blends can have as low as minus 10% raw tank to wheel CO2 emissions compared to the regular diesel. And then if we take into the account well to tank part, as in the previous cases, it's much more sustainable. Actually, studies show that HVO is more has lower life cycle CO2 emission than EV driven in Norway, and E85 for spark ignition engine has slightly above that level. And then we see the effect of also cetane number, density, and lower heating value on the heavy duty engines. The effect of the HVO is stronger in smaller size compression ignition engines than in the heavy duty engines, but the trend is the same. So CO2 emissions are lower, and we can see that over here as well. Then going to marine and marine side, we see the effect of viscosity, density, and lower heating value on different kind of SVO type, straight vegetable oil type of fuels like soybean oil, sunflower oil, also here palm oil, animal fat. And for aviation, similar properties actually survived as in the case of the marine. And we see here most of the fuels are synthetic paraffinic kerosene, but also synthetic isoparaffins, HEFA, ATG, and so on. ATG, alcohol to jet, is actually also synthetic paraffinic kerosene. The model has also very high R-square in the case of the aviation. So we took those all models and made the user-friendly tool, which I will show a little bit later. But then few our observations. So good fuel candidates by 2040, realistic from our perspective. So for aviation, we see synthetic paraffinic kerosene made out of the it could be HEFA, alcohol to jet, and so on. So this kind of drop-in solutions are the one we see the most applicable. Then marine side, in the marine side, as Brian and Professor Marty Larmi mentioned already, hydrogen has a big potential. And the good thing about the hydrogen is that both no sulfur and no carbon. So it could be blended also with the LNG. So there are big possibilities in front of the hydrogen. Then DME is also, but DME is has high price and low availability, so it's rather too premium fuel for marine side. Maybe more for the heavy duty. Then we see the biogas. Of course, now many ships are switching to LNG, and this creates a drop-in possibilities for LPG, so liquefied biogas. LNG, the good thing is that it's cheaper than heavy fuel oil, and it has no sulfur content, and there is some moderate infrastructure already. In marine, we need to have infrastructure. We need to have this availability. It's very important. Then methanol, as in the form of the, for example, MD95. So diesel-like combustion, 95% methanol, 5% strong ignition improvers. This is something that is possible and it's under R&D. But what's in marine emerging now, and it's a pretty promising solution, is this biocrude from hydrothermal liquefaction. This is something that is now in a pretty low technology readiness level. It requires effective upgrading and so on, but it's very promising substitution for the heavy fuel oil. Then in the light duty vehicles, we see the electrification, of course, as mentioned, the easiest in the light duty vehicles. So we see electrification going, but electrification alone will not solve the problem. We need drop-in fuels, we need dedicated powertrains. And here, for example, compressed biogas is an option. We have CNG infrastructure in Europe, for example. This could be used pretty straightforward, both for heavy duty and for light duty as a compressed biogas infra. Then we see methanol. Methanol is excellent fuel, actually. It has very high RON, very high heat of vaporization, so engine cooling effects. It's very good fuel. The problem with methanol is that we need dedicated engines because and we need standards because EN 228 allow only 3%. But this has been proven in China. There are cars running on the pure methanol even. So they need basically corrosion resistant engine materials and fuel supply materials. And then it's possible to use methanol. For the case of the heavy duty engines, it's a little bit different. So what I said in the light duty spark ignition way, but in the heavy duty, we need, it's more like the MD95. And then ethanol, of course, flexi-fuel vehicles known to everyone. The good thing is that the additional cost of the powertrain is just 180 euro compared with the 2,265 euro for the whole gasoline powertrain. So it's not, let's say, very big difference, but these flexi-fuel vehicles are mature technology and they could be easily applied. And for the heavy duty vehicles, we know the case from the SECAP, Scania ED95. So 95% ethanol, 5% strong ignition improvers. But then again, it's a dedicated engine, compression ratio 28:1, so way higher than in the case of the regular diesel engines. For the light duty also renewable gasoline is something that is under research. So something that could be something like HVO for diesel, so renewable gasoline for the substitution for the regular gasoline. And of course FAME, but FAME is not the best, is not, let's say, game changer over here. It could be blended only 7%. Above that level, there are different compatibility issues. So, of course, feasible, but limited. And we need always to look into the infrastructure and fuel compatibility when looking into the time frames when we are able to achieve given targets of the decarbonization. We need to see that, okay, if we consider some fuel, whether it needs dedicated engine, small retrofitting, drop-in, and where is the infra. And the end-use analyzer. So if you go to the advancedfuel.aalto.fi, after a very simple free registration, you are able to proceed directly to the tool and do. And here you have option to select the transport mode, surface, transport sector, fleet type, engine type. And then you have two options: either go to predefined fuels, so you can see some fuels that standards already exist or they are known, and then you can go, for example, to the custom fuel. But when you choose defined fuels, you select fuel, you click calculate. For example, here we have HEFA, synthetic paraffinic kerosene, 50%, and we see the change in the fuel consumption and in the CO2 emission. And also you have whole description, recommendations, and references where you can reach for more details how what's happening on the back end. Then custom fuel. Here, if you know fuel properties, but raw fuel properties, you can select raw inputs. And then you have reference fuel over there. You can change the properties of the reference fuel. They are, in the case of the jet engine, those are the properties of exact jet A1. And then alternative fuel. So you are just writing there, for example, I don't know, net calorific value, mass-based, say 40, density 800, and it calculates the relative change and computes the change in the fuel consumption and CO2 emission. If you don't know the raw final values of fuel properties, you can select relative inputs, and there you can just write that, okay, net calorific value changes 5%, so just type 5. Density, for example, decreases 3%, you just write -3. So if you don't know the absolute values, you can go for the relative. And then if you wish to, for example, look for the component, like methanol or something, if you add methanol to gasoline in 30% in spark ignition engine, you can select, you can go to the fuel blend, select the component that you are interested in, and then write the concentration and calculate and see what's happened with the fuel consumption and CO2 emission. Yeah, we published part of our models. Another part is on the pipeline in the publishing process. So I will share maybe later on this presentation with you, so you can reach out if you are interested to read more. And some few ideas for collaboration that just came to my mind. That if we find common interest, for example, LCA analysis, energy scenario development, what are the things that are from the real perspective possible when we speak about the technology advancement, when we speak about the infrastructure and the whole change in that respect. We need to take into account many aspects. So maybe we could be of some help. Some of our expertise could be here utilized. Then environmental impact analysis, low cost effective decarbonization pathways. I think this is the point that we could also be of some help. Then I was thinking that some databases could be a good thing, to create common databases that we could utilize. Perhaps you could utilize ours for your modeling or some further analysis, or we could also utilize some of the databases that you are able to share with us. Then exchange of modeling methodologies and tools. This could be also one interesting area. And what I think is what I create right now is the list of available tools for various energy analysis. So we can, after I finalize this list, maybe I can share it with you, and you could also add some tools that you know and that you recommend, and then we can have some nice, let's say, one Excel file when we have different good tools that we could utilize for different purposes. So that would be all from my side. I want to just highlight that all the research that I presented is not only my part. My good friend Michał Wojcieszek is working hand in hand with me with this all models, and Professor Marty Larmi and our advisor Ossi Kario also. So thank you very much for your attention, and I would be happy to hear your comments and questions if there are some.
Thank you very much, Yuri. That was excellent. A very useful presentation of your work, and then also with the suggestions at the end in terms of areas. I have one quick question just on, there was one part of I really enjoyed that slide where it talked about options and compared different options. And you mentioned that LNG is cheaper than HFO.
Yeah.
But it wasn't clear to me about LBG.
Yeah, LBG is more expensive.
Okay, because it was in that section. Okay, thanks. That was just a clarification. Okay, we've got a couple of suggestions coming in for the chat. I want to open the conversation now to the floor. As I've indicated, I wanted people to put in questions either in the Q&A or in the chat. We've got one suggestion from Tom Kober, which would be that an interesting collaboration could focus on decarbonizing aviation and new fuels specifically for this sector. And I think Tom sent that before seeing your slide where you showed the range of options for the different transportation modes. My own sense is that we could benefit actually from all the modes, you know, particularly as Tom says, aviation, but also for marine transport and heavy goods vehicles in particular, because those are the areas where there is most uncertainty in some sense. And there's a number of considerations in that. One is, you know, if we have a limited bioenergy potential globally, what's the best use of that bioenergy? And so obviously in transportation you would look at aviation first, because you had a very nice slide showing the prioritization in terms of where liquid fuels are needed most. And so if you want renewable liquid fuels, that suggests potentially, if they're of a renewable source, that you would prioritize there, and then marine, and then heavy goods vehicles. One of the challenges, of course, is in light of the Paris Agreement and the significant increase in political ambition on mitigation, is the role of bioenergy with CCS to provide negative CO2 emissions, to enable other parts of the energy system to evolve. So there was an interesting report a couple of years ago recently by the International Energy Agency looking at the future of trucks. Because if you look at that prioritization in transportation, trucks are probably lower down than aviation and marine in terms of making use of limited bioenergy. You've got that increased demand from bioenergy with CCS for bioenergy, and of course we've a limited sustainable bioenergy resource potential internationally, albeit it still needs to grow. So these are interesting questions that when we look at things in our energy systems models, these are some of the things that come out in the mix, if you like, because we look at all energy service demands, so transportation, electric and heating, all the energy servicemans that draw on those energy carriers or energy modes. And we look at all possible fuel inputs. And then we would look at things generally on a national basis, sometimes on a multinational like EU, sometimes on a global basis, and sometimes on a subnational basis.
Mm-hmm.
And what our model does is takes projections of technology performance, technology costs, technology emissions related data, and optimizes, so finds the least cost solution to meet our future energy needs with the range of technologies that are available. And then if we add in constraints relating to emissions or carbon budgets or something like that, then that pushes obviously the energy technology choices towards the lower and lower emission choices. And that's why I was encouraged to see when Mark, in your slide at the end, you mentioned databases, because that is a way in which we could, I think, share information would be if we had access to if we could share some of our templates of data that we use, and if we could access some of the data arising from your research, and then do joint scenario development to test and to see. And in that way, we could use your data in our models, but do the scenario development together so that we could share the insights that come from the scenarios. So I think Tom's suggestion, I like Tom's suggestion on aviation and new fuels in aviation, because that's a critical area in its own right. And sometimes it's neglected when we look at national modeling, because we don't normally include certainly international aviation in the country's emissions kind of requirements or policy. The UK have done so recently, but normally it's not the case. And
when thinking about the aviation, actually, one thing that people sometimes don't know is that the sulfur limit for the one. This is something that is a problematic, and it's high. And when we use, for example, sustainable aviation fuels, we get rid of this problem.
Yes.
At the same time.
And I think that's another dimension to, in a lot of our analysis, scenario analysis, we focus on CO2, but in our work program for the next few years, we have we want to go further in looking at other sustainable development goals. So clean air and air pollution, and that interaction between, it's a very important policy consideration that aligning climate mitigation with clean air. And that raises questions around sulfur, around NOx, around the other pollutants. Particulates is a key one as well in that regard. And so when we're looking at fuels and we're looking at combustion, the CO2 performance is very important, the fuel efficiency is very important, but so too, in a growing way, is the air pollution considerations. And maybe to also bring Marty into the discussion, because I see in the chat, Marty, you suggested that the IEA combustion is open to collaborations, and so starting a collaboration is easy. We have a different process in the sense that, and the timing of this is useful because we have our executive committee meeting later today. So we'll be able to, and that's why we timed this meeting before the executive committee meeting. So any suggestions from the workshop can be brought into the decision-making processes. And we will feed back to you after today's deliberations on possible next steps. I think from my perspective, I really appreciate the openness with which you've come to this meeting and the offer of collaboration. The fact that you have this task is very timely. I think this shared analysis task, systems analysis, sorry, task. And so some of the areas, hydrogen blending with natural gas or biogas, vehicle fuel economy, solid fuel combustion, and aviation fuels, there are 4 topics. And perhaps this other one of this how CO2 emissions reduction and air pollution, how they interact, how they with the different fuels. I don't know if that's something you've looked at closely. It sounds like it came out of that analysis, but I wasn't fully clear if that's the case.
PM emissions, particulate emissions, they go down with HVO when you use HVO in the regular diesel.
Yes.
So you have both lower CO2 and PMs.
Yes, well, they go down, but another consideration in the context of choices would be how far do they go down, and how do they compare with other options like biogas or electric, you know, those kind of considerations. So I appreciate they go down relative to diesel, but it's how do they compare with other competing choices is the other dimension. So the yes, and Anna, because we have a project at the moment. Actually, again, it's the timing of this is useful for us, and Anna has kindly put into the chat. So we have a process where we're developing templates for bringing information into our times model. So that's another opportunity for collaboration. So I think certainly from I was as I mentioned at the start, I saw opportunities before we discussed. I see greater opportunities now that we have discussed. For us, it's important increasingly to look at combustion. As I say, there's a lot of focus in energy systems analysis on the electrification part of the story, which is crucially important. But equally, I think there needs to be more focus and more of a spotlight put on combustion and the different fuels. And sometimes we talk about renewable fuels as if it's one thing. And I think you nicely showed that there's a broad canvas with different considerations associated with each. So
and again, you know, the one of the first slides of mine, the magnitude of the decarbonization challenge. This is really something that is very important, that we are not able, there is no silver bullet. We are not able to go with one sustainable technology. We should look whatever is better today than fossil fuels. We should go full throttle with decarbonization, both with the renewable fuels and with the electrification, hand in hand. Because the challenge is so big, so big. And
yes.
we have just 10 years to stop this climate change catastrophe. So
yes,
if it goes like it is, the consequences will be big. So we have no luxury basically for choosing.
Sure.
Yeah.
But I think one challenge is within that, and that's fully accepted. As I say, what we see is that if we maximize land use for renewable fuels, we still have a challenge in terms of the scale. So there isn't enough renewable fuels
Yes.
Available, or there will not be enough renewable fuels available to fully meet all of what we might. So that's where because our analysis takes an optimization approach. That's where it's useful to compare. Now, cost is only one thing, of course. It's only one part of the consideration, but it's a useful one, and the policymakers certainly it engages them if we talk about least cost analysis.
Yes.
So meeting these ambitions with least cost analysis we find as a useful way to engage in discussions. But that doesn't mean that the options are cheap, and it doesn't mean that we also find that if we start excluding things, excluding fuels, excluding technologies because of preferences, then the costs go up, because of course we still have to achieve the emissions reduction, but so the ambition remains and the costs go up, and that can be a useful way of discussing renewable fuels, particularly if depending on the politics of the discussion.
You know, one thing also, for example, electrofuels and
yes,
short chain methane, methanol.
Yes,
methanol, for example, produced out of the CCS also. Point.
Yes.
For example, sector coupling, so bridging metal production, you have a lot of CO2 streams of the CO2, stable streams of the CO2 from the metal production, like ArcelorMittal. Bridging this with synthesis of methanol, so methanation process, renewable electricity combined with this, and so there are. We don't need to look strictly. This is why I say renewable fuels. So we do not need to strictly look into the biofuels.
Of course, yes.
But also we can look, for example, into the processing even the waste, municipal solid waste, plastics, everything what is of waste, what is anyway will be disposed somehow. Could be turned into the fuel. I mean, possibilities are pretty wide, so it's good area for common discussion.
Yes, I'd like to give the last word to Marty. So we will have our discussion, our executive committee meeting, as I mentioned, later today. So we will discuss this and come back to you with something more concrete by way of a formal response. But I'm very enthused by our discussion, by the collaboration that I can see and that what people are suggesting. So I'm very enthusiastic, but I'd like to give the last 2 minutes to Marty, please.
Okay, thank you, Brian. Actually, I'm pretty excited about our collaboration, and actually our combustion TCP sits on a very big amount of data, but it's distributed all over in our projects, and takes a time before we can gather some kind of databases or something like that. But it would be very helpful if we get wishes from your side. What could be helpful for your system analysis? Then it's much easier than for us to gather that kind of data and have a look if there's something lacking, and we could discuss within our TCP how to fill these kind of gaps of data. And actually, I'm excited about the collaboration with about this aviation, especially, and this hydrogen blending in natural gas or biogas. That is pretty interesting, and also these solid biofuels and overall fuel economy. These are all excellent ideas, and we are happy to share our results with you. And then this data what we have and which we could create, and then it's useful, and then it has some kind of impact. So I think this is very important, not to have the data within us only, but to be used somewhere, to be utilized.
Great. Okay, well, that's excellent. And I think Anna has a specific suggestion in the chat around that, as I mentioned, with this subres project. So regarding this template or the format of the data that we use, so that can be an early action.
Okay, very good.
So I want to thank you very much. And as I say, we'll give you further information following our executive committee meeting later today. But I really do appreciate the time you've made available today and the presentations, and more particularly the openness and the willingness to collaborate. So thank you very much. So at that point, we'll close this session, and we'll have a short break, and we'll be back in 15 minutes for session 2 of the workshop. Thank you.
Okay, thank you.
Bye-bye.
Bye-bye.
Bye-bye.